Okay, our next speaker is Alessandro Rivitti, and he has recently completed his master's degree, and he's going to be starting a PhD at the University of Roma Tor Vergata, also working at a network packet processing company that is called Axbryd. And he tells me that this is his first ever conference. So what a great way to be introduced to coming to conferences and to stand up and give a talk. Okay, Alessandro, take it away.
Hello, so thank you for the presentation. My name is Alessandro, and today I'll talk. My talk is focuses on a very pressing problem. The purport speed of network interface card is increasing. In fact, it's increasing to over 100 gigabits per second. In the past years, you might have used 100 gigabits per second devices, but it won't be uncommon in the next years to use the 400 gigabits per second devices. And the terabit Ethernet in this context is plausible in the near future. So in order to perform efficient network packet processing, we can't really rely anymore on mere software implementations of network functions. We have to carefully leverage the hardware features of the device itself. So when we were thinking about this work, we noticed two main aspects. On one side, we know that NIC vendors are generally smart people and are starting to implement, for some good reason, reconfigurable hardware inside their devices, such as FPGAs. In this way, you could actually insert your network function inside the NIC itself, leveraging the FPGA. However, I'll state the obvious when I say that FPGA programming is hard. I've done it myself. The second thing we noticed is that eBPF is a programming language that's based on C, and it boosted in traction recently inside the networking community, mainly due to the fact that the XDP hook can be used to program network functions. So we decided to build upon these two main topics, eBPF and SmartNICs, and we developed eHDL. eHDL basically is a high-level synthesis tool that takes unmodified eBPF programs and generates custom designs for the NIC. In order to do so, eHDL is based on eBPF, which makes it much easier to use than most high-level synthesis tools. The core design of eHDL is an IP core that we embedded inside Corundum, which is a programmable open source datapath. All the tests of eHDL have been performed inside the Xilinx Alveo U50 with a 100 gigabits per second link. Over here, I show a basic scheme of what eHDL does. eHDL is basically a pipeline of stages where at the input and output, we have two streams of packets, and every single stage of the pipeline can either perform changes to the packet, to the registers and stack of eBPF, and every single stage, again, can access to the eBPF maps, which are persistent memories. But some of you might know that there's already been extensive work on high-level synthesis tool. Might be asking, what does eHDL has to contribute over already existing high-level synthesis tool? I'll say that eHDL was developed with networking purposes only in mind. In this way, we avoid the general purpose loss of context, let's say. In order to comment on this, I here performed a comparison of eHDL with VT's HLS. Here is a simple protocol counter code written in eBPF. It basically takes packets, and every single packet is classified by their Ethernet protocol, and the count of those packets is kept inside the eBPF maps. The same design was built using VT's HLS, and over here I report the code to do that. We not only see the increased number of line of codes, but the most important thing to notice is that in order to use this kind of high-level synthesis tool, you need to have hardware expertise to know how to use the AXI word constructs or pragmas or things like that. This complexity is completely hidden to network engineers when using eBPF codes. Over here, right now, I show how simple eBPF code is translated into a pipeline of stages. So again, this is the protocol counter. We simply compile it using standard LLVM compilation step. The object code is then analyzed and parallelized, and every single parallel instruction is translated into a pipeline stage. Over here, I show an overall example of the pipeline, and it's confusing, so I'm only going to show one stage of it. And we see over here how the parallel instruction is translated into this kind of transformations that happen between a stage and the other of the registers. Of course, during the development of eHDL, we faced several challenges and managed to obtain several optimizations. However, in order to keep the presentation brief, I'm only going to talk about one optimizations that we managed to achieve. But I encourage you to check out the full paper to learn more about the work. So, as I described to you, eHDL is based on a pipeline of stages that can access persistent maps, the eBPF maps. What I just described to you is a potentially data hazardly architecture, mainly due to the read after write and write after read problems. In order to deal with them, again, we statically analyze the parallel code. Every single load and store instruction has been labeled to be either referring to the packet, the stack, or the eBPF maps. So whenever during the static analysis we highlighted the potential of data hazards, we deployed two hardware primitives. So over here, I show how we solved the write after read problems. Basically, between the writing stage and the map itself, we inserted a buffer, a write buffer. In this way, the red data won't be the newly updated one, but the actually requested one. In order to solve the read after write, we inserted this kind of flash evaluation block. Basically, it keeps track of all the red locations inside the map. And whenever the pipeline requests a write instruction, the writing address is compared to the previously read ones. If these two addresses collide, a flash of the whole pipeline is requested up until the writing stage. In this way, the stale data is removed from the pipeline. So with these two basic hardware primitives, we manage data consistency inside the eBPF maps. So I turn over here to an evaluation part of the work. Here I roughly report some values of the performance increase we managed to achieve using the Vergata, which is an open source eBPF code for a packet filter. We, of course, implemented the Vergata using eHDL and a standard CPU implementation. We managed to achieve an increase in performance in terms of throughput, latency, and energy consumption. But I reported here the overall zero engineering time, meaning that in order to achieve this custom design, only the use of eHDL was requested, only the use of a compiler rather than having to allocate some hardware engineer expertise for some time. Of course, eHDL wasn't only evaluated with Vergata. We've evaluated with 4 other more network functions for this work, which are a firewall and a DNAT function, and the standard router and tunnel of XDP that are already inside the Linux kernel. These 5 network functions have been implemented by the eHDL pipelines, by HXDP, SDNet, and an NVIDIA Bluefield. I'll go briefly over them. HXDP is a soft core for the FPGA that's optimized for eBPF programs. SDNet is another high-level synthesis tool that's based on P4. And NVIDIA Bluefield is a simple DPU where we implemented these eBPF programs. So I show it's not that clear by the graphs. However, eHDL performs at line rate for all the 5 network functions and has an overall latency of around 1 microsecond. The HXDP, we can see how an implementation of a single core requires more FPGA resources than all the 5 eHDL pipelines. But it's much more interesting to see that HXDP performs worse in terms of throughput as well. For what concerns SDNet, it's important to highlight that, of course, it has similar performances in terms of throughput and latency. However, using SDNet, there wasn't a simple way to implement the DNAT function, mainly because it's a stateful one. And in order to implement stateful functions with P4, that's not like such an easy task to do. but we managed to achieve stateful functions in HDL because we managed data consistency. And compared to the NVIDIA Bluefield, we can simply see how all the 5 network functions performed worse. In conclusion, today I presented eHDL, which again is a high-level synthesis tool that takes unmodified eBPF programs and generates custom designs for the NIC. I report here that it requires about 0 engineering time. It's simple enough to use since it's based on eBPF. That's already well known by most network engineers. It guarantees line rate performances on most network functions. It also handles stateful functions, and I encourage you to check out the paper for more details. Also, I'd like to mention one thing. During today's poster session, I'll be showing a demo of usage of eHDL using the Vergata network function. So that's it. Thank you for listening, and I'll take your questions now.